The objective of this presentation is to get insights into the diffusion of guest molecules such as carbon dioxide, methane, and hydrogen within chabazite zeolite. Here's the structure of chabazite. Consists one unit cell of chabazite, has 6 cages. Each cage is separated from an adjacent cage by narrow 8-ring windows. But the cage volume for chabazite is slightly larger than for DDR zeolite, but significantly smaller than for fwagicite. Here are the window dimensions. This is 3.8 angstrom in this direction and 4.2 angstrom in this direction. This table provides further structural details such as the dimensions of the unit cell, the framework density, the pore volume, and the surface area. The chabazite framework has some degree of flexibility, and the framework flexibility has some influence on the motion of molecules from one cage to the adjacent cage. And for further information on the influence of flexibility on diffusivities, you can consult this reference. In order to gain insights into the diffusion of molecules in chabazite zeolite, we conducted MD simulations at a temperature of 300 degrees Kelvin. The simulation methodology and the diffusivity data are available in the published literature. On the basis of these MD simulations, we constructed animations to gain some qualitative insights into the motion of guest molecules. Let's look at hydrogen methane. Hydrogen is a much smaller molecule and it can diffuse from one cage to the adjacent cage much more quickly than methane. Consequently, for separating these mixtures using a chabazite membrane, the permeation is selective to hydrogen because of the significantly higher hydrogen diffusivity. The situation with regard to CO2 methane is somewhat different. CO2 is a long pencil-like molecule and diffuses lengthwise across the window from one cage to the adjacent cage. The lengthwise diffusion is understandable because the cross-sectional dimension is just 3.1 angstrom, whereas the diameter of a methane molecule was 3.7. So CO2 diffuses much more quickly than methane. The absorption selectivity is also in favor of CO2, and the chabazite membrane has a high CO2 methane permeability, making this material of potential practical use for CO2 methane separations that is important in natural gas purification. The story with CO2 hydrogen is slightly different. Hydrogen, being a much smaller molecule, has a much higher rate of intercage hopping, and the diffusion selectivity is in favor of hydrogen. But the absorption selectivity is significantly in favor of CO2. The net result is that the chabazite membrane is CO2 selective. Chabazite also has applications for separation of water, alcohol, and alcohol mixtures. Here is an animation of the diffusion of methanol and ethanol in chabazite. And what you will note is there is a significant degree of clustering between methanol and ethanol due to hydrogen bonding. A methanol ethanol cluster diffuses much more slowly than either methanol or ethanol because of mutual slowing down. And such mutual slowing down effects are of significant importance in the separation of alcohol mixtures.